Hello guys, my name is Arun Tyagi and today I'm going to discuss about one of advanced data structure. The name is, as you can see on the screen, is Fenwick Tree, or we also call it binary indexed tree. Now, to be very honest, to understand Fenwick Tree, first time it's not easy, you know. Though this is again another data structure which once you understand the writing code for it is very easy. So like if you have seen Dark on Netflix, the series Dark, first episode you have to watch, and once you watch the first episode, rest of the episodes will make you sit there. Very similar to that, I will request you to just do 2 or 3 exercises with me, and Fenwick Tree will be a cakewalk for you. Okay, so let's just start with simple exercises. So if you can see, I'm having a simple array here, an integer array. What you can think of that we are given with some values, integer values into that array. Now I'm leaving the first place empty. That is why I'm representing it with a null or empty or x, right? So leave it empty. From first index, I'm having these values. Now one more thing I wrote is, what is the binary representation of these indexes? Like for 1, it's 001. For 2, it's 010, and so on. Now we are done. Now, what we're gonna do is, let's do a simple exercise. So we have to update another array called ft. For that, how we gonna update this is, see at first position what we are having 5. So at first, so this zeroth index I will replace it with 0 because we are not going to touch this one. At first index, I will simply keep 5 first. I will copy it as it is, right? And then I will see one thing. What is the binary of index of this? So binary of index of this is nothing but 001 if I'm writing 3 bits. Now I will take LSB of it, the least significant bit set, right? So this is this. If I will take only this and rest of the things, even if there would have been some one here, I will ignore it and I will just simply take this one. So if I will take least that set bit here, so it will be nothing as zeros and then 1 at the last place, right? Now if I convert this into integer again, it will be nothing but 1, and right. So we are having it. What I will do is, what I'm now saying here is that from first index, take these many numbers, add them, and place that value here. So in this case, because it is nothing but 1, I placed it 1 only. Now let's move to the second index. For my second index, the binary of this is 010. Again, my LSB here is here. So if I just take LSB, it will be nothing but zeros and then 10, right? Then if I convert this into integer, it will become 2, right? So it became 2, and what by this 2 we mean, from this index, the index which we were talking about, from this index, take 2 previous element including this and add them and place at the second index, at the second index in ft. So if I take 2 values, so these are like 1 and 5, so sum is 6, so I will place that 6 here. Now I will go with 3. For 3, my binary is 011. If I take binary with LSB, it will be 001. Now integer of this is nothing but 1, right? Now this means that from this index, take one element and add that and place that here. So if we are taking only one element, this will be nothing but copy this value here, so it will be 3. Okay, and at the same time I will write also that here I took only one element, I took uh, two elements here I took again only one element. This is just for the explanation, we don't need it in the real code. Now let's move to the next one. Next one is 4. So for this my binary will be 100, and if I take LSB it will be nothing but 100 again, and my integer of 100 is nothing but 4 again. That means from here I have to take 4 values. So I will add these 4 values. So 6, 10, 15. So I will replace this with 15, and I will also write that here I took 4 values, sum of previous 4 values. Let's do the last one, which is for 5. So it will be 101. If I take LSB, it will be 001, which is nothing but 1. That means I have to take only one element. So by one element, we will simply take 2 here, and we'll write that we took one element. So this was our first exercise. Don't think of, we are talking about Fenwick tree. We are just doing some exercises, and those simple exercises will be ultimately converted into our the real Fenwick tree. Now let's move to second exercise. So I copied that our last array here again. And yeah, if you are not doing this exercise with me, I would highly recommend you to uh, grab a pen and a paper and do it with me. Then only you'll be able to, make full benefit of it. So now the second exercise is that from this given ft array, now we are ignoring the main array, and we'll just focus on this Fenwick tree array which we built, right? So let's suppose we received a query that give me prefix sum. So I'm calling it prefix sum, so let's just call pre-s from index 3, and by index 3 we mean this index 3. Okay, so if we have to do it, how we will do it? We'll simply get the value of third, that means whatever is the value in my ft at third place, which is nothing but 3, this value, plus, because this is just the value of one element, if you see here, plus here we are in the previous element we have values for two elements, right? So plus value of f2, and value of f2 is 6. So our answer is 9 for prefix sum 3. Is this true? Let's just check. So in our original array, from here if you see, the sum is actually 5 plus 3 is 8 plus 1 is 9. So yeah, we are getting it. Try another one. Let's see, we need to get prefix sum for index 5. So for index 5, we will get value of ft5, which is having only value of one element, and the value is 2. Then plus previous one is having for 4 elements, so ft of 4, and the value is 15. So answer for this is 17. Is it true? Let's just check. So till here we had 9. 9 plus 2 is 11, plus 6 is 17. So this is also fine. Now if you see how we are calculating this PreSum, right, from Fenwick tree, it was coincidental that we just added two elements only, and those were consecutive. But what we are actually doing is, so if we have to calculate pre-sum of index 5, how we gonna do it is first blindly copy value of ft5. Then what is the binary number for 5? It is 101. Okay, if I take same LSB from here, then it will give me 001. Now for 001, integer value is 1. So I will do 5 minus this 1, which is nothing but 4. So I will add another value called ft of 4. Now binary number of 4 is 100. If I take LSB, then also I will get 100 because there is only one set bit. Integer of 100 is nothing but 4, right? So I will do this 4 minus this 4, which is nothing but 0. So I will do plus ft of 0, and ft of 0 is always 0. So once we reached to 0, that is where we will stop. This is our second exercise, and you can try it with a bigger index value also. So you will see that how we can calculate a prefix sum via going in this pattern, where we are taking binary. First we are taking that index itself, then we are taking binary of it, taking LSB, reducing that value from our index, and taking that after it. So likewise we will go up till we reached zeroth element. This is our second exercise. All right, let's move to exercise 3. So I will copy array here again. So our array was, we'll just write a equals to, first place was empty, then we had 5, we had 1, we had 3, we had 6, and we had 2. We made a Fenwick tree also from this, and Fenwick tree was, first place was always 0, then we had a 5, we had 6 here, we had 3, we had 15, and we had 2. Yep. Now so normally it is so now let's suppose the exercise which we have to do is that at a given index, let's say idx, in whatever was the original array, because you are supposed to work on original array and then answer the queries. What at given index, just add a value v, right? And that v can be anything, -1, +2, like that. So for example, just take that at index 2, add a value 2. So v is equals to 2. Now how we are going to do, so in original array, though we don't have to do anything, but for symbolic, I will just do it. So in place of 1, because I'm adding 2, it will become a 3, right? So when we changed it to 3, ft should also change, right? And multiple values should update, so that the prefix sum query which we were answering earlier, that should be correct even now when you modified the array. Now how to do that? So for that, pattern is same which we applied in calculating the prefix sum. How it is that first go to the index which is given index and directly add this value, plus equals to v, right? So here v is 2. So at second index, which is 0, 1, 2, 3, 4, 5, this one, in place of 6, it will become 8. Now you cannot stop here, because that prefix sum should affect other values also. So how to go forward from here? First you did this blindly, then you will take what is the binary number of this 2. So binary number of 2 is nothing but 010. We'll do the same thing, take LSB, it will give us nothing but 010 again, which is a 2, right? So last time we did a subtraction because we were calculating prefix sum. So from a given index we were going backwards. Here we are adding a value, so we will, so that prefix, that sum will affect the values after it, so we will add it. So 2 plus 2, so this 2 plus this 2 we will do, it is 4. So what we will do is at ft4 we will add the value. So now here at ft4 we will add 2. So this 15 will become 17. Now we will not stop here. What is the binary number of 4? Binary number of 4 is nothing but 100. If we take LSB, it will be nothing but 100, right? And this is also nothing but 4. So this is coincidental that you are getting 4 for 4, right? For index, you are getting the same value to add. For 5, you will get 1, right? So we have seen it earlier. So anyways, now we got 4 here. So this 4 plus this 4 we will do, so we'll get 8. So that means at ft at 8th index we have to add the value, but 8 is actually greater than the size of this array, so hence we will stop. We need not to update any further value. That's it. So we are done with third exercise, and now we will conclude using these three. We are actually almost we are actually done with the Fenwick tree. So let's now just create that understanding of Fenwick tree. Let's just conclude what we did so far and how it is helping us, right? So normally Fenwick tree, segment tree, these trees are used for range sum queries. What this means? This means that you will be given an array, and you will receive two kind of queries. One is that you will receive a query that update a given value, increment or update a value in the array. So that will be the one thing you will do. So it's like you have to update the array. Second you will receive is in a given range, means you will be given a left and a right, and you have to return the sum between this range, this given range, right? So if somebody would have asked for sum of a given range, and if array is not getting updated again and again, then this would have been very simple. So if let's suppose we are given a static array. By static array means we have an array and it is not changing. So what we would have done is we would have calculated a prefix sum array, and once we have prefix sum of anything, and if you ask me to give again and again give me sum of some given range, what I will do is I will get prefix sum of right, then I will get prefix sum of left minus 1, right? And once I will subtract from prefix of right to prefix of left minus 1, then I will get the sum of that given range. That would have been very simple. But because you are changing the array again and again, it's not possible with this prefix sum array anymore, because whenever you are changing a value, you have to update all the values after it, right? And hence the complexity will increase. And we saw that updating, when a value is changing, updating in Fenwick tree, what we just discussed, is very easy. Okay, anyways, so before I write code for it, or pseudo code for it, one more thing is, so you have seen that what we are doing is, let's suppose a given index, idx 5 we are doing. So we were doing one thing, we were getting binary of it, then we were getting a number with only LSB set, and for this integer then we were subtracting from 5 this one, right? So we are doing this operation. If you are not used to of doing bitwise operations and writing code of it, then this will be a little you can say tricky for you. So you can just just write down one formula that will help you. So to get this one, any number, a number where only LSB is set for a given number. So like for this one, my answer should be all others will be 0, and then this one 0. So a number with only this one set, right? So to get this result, the formula is we need to do idx. If idx is my number, bitwise AND operation with minus idx. This one you can just remember it, right? And you can check how it is happening later. For now, just ignore that complexity. All right. So what we did so far, try to write it in the code, right? So let's call it a class. So let's call it class Fenwick tree, or I will call it binary indexed tree. So BIT I'm writing, right? And I'm just writing the pseudocode. First thing we did is update a value. So how we updated a value is, let's say void, because you are just adding a value, add a given value v at index idx. This was my first kind of operation. When somebody asked this, what exactly we did? First, we went ahead and in the Fenwick tree array, which is nothing but it will be a global array in this class that you can do. I'm just focusing on the function. So at in FT, uh, okay, don't even do that. Actually, we updated the multiple places. So let's just write a while loop. Till when we did it? Till the idx was actually less than or equals to the size of my array, right? And why size? Because we are taking first value, zeroth index we were not using, so we were doing it from 1. So we will always take size of the array to n plus 1, so that is why we are going till n. And these are simple things which you, even if you will make mistakes, you can debug them easily. So we are going till the very last index. And how we are doing? First, we were doing that at that particular index, simply increment the value. That is what we did first. That at ftidx plus equals to whatever is value given to me. Second, we did all that thing that, in my idx, subtract a number which will come after getting a number where only LSB is set from with that index. So like I said, formula is, so because we are doing subtract, so this is like minus equals to, and the formula was simple, that idx bitwise AND operator with minus idx, and we are done. This is Fenwick tree update query. Point update query is done. It was as simple as that. Okay, yeah. So I think for addition, we were actually in the array. If we go here in Fenwick tree, so whenever we were updating any value, we were updating that index, and then we were going forward with this formula. So for addition, this is actually not minus equals to, but this is plus equals to. So we are increasing the idx until this is reached to last one. Now, second kind of queries which we support in range sum is that basically given a range and just return the sum of that range. So if I write code for it, this will be a simple one line that you have to return an integer. Let's call it simple range sum, and you are given an L and R. Both are you have to include L and R also in the response. Now this will be very simple, that simply return, like we discussed earlier, simply return if you have prefix sum. Let's call it prefix sum, and we will define this function prefix sum of R minus prefix sum of L minus 1. Okay, so this will be just one line. Now we can define this prefix sum. So for prefix sum, that will be a function. Let's call it prefix sum where you are passing simply one idx that give me prefix sum from this index, including this index also, right? So for that we discussed how to calculate that. Let's suppose s is where I will store the sum, so in starting s is 0, right? And we can do those checks, like if idx is negative, like in case of my left is in case of my left will be 0, so l minus 1 will be minus 1. So we can check here, if idx is invalid, then simply return 0 sum, right? But that you can handle. I'm just writing the specific code. So what we discussed is, while my idx is greater than 0, so you greater than equals to 0 also you can do it, greater than 0 also you can do. It's up to you, because we know in Fenwick tree at at 0th index there is a 0 value, right? So it doesn't matter whether you write greater than or whether you write greater than equals to. Okay, so we wrote this condition, then we will do simply one thing: s plus equals to, we are increasing our s with ft at whatever is the value at idx. That's it. Now prefix sum is lying between current value and some addition from the previous value in the ft array. So how to go about that? We just need to decrease our idx. So we will do idx minus equals to same thing which we did earlier, idx bitwise and with minus of idx, right? This is your loop. In the end, simply return some value. So you are done. So in fact, that is also checked here. If your idx is negative, then this loop will not run at all, and simply it will return 0. So we are done. So this is actually done. Your Fenwick tree is done. We'll use this code, which is just 3-4 lines here, one line here, and 3-4 lines like here, one this line, and 3-4 lines with this function. And we'll do a range query sound which used segment tree, which is solved by using segment tree. So we will solve that using this Fenwick tree. Okay, perfect. So that's it. So this is I'll conclude it here, that this is what Fenwick tree was. It is very simple, right? And complexity wise, so to add a value, this is the loop which is running, and this actually, with the speed with this idx will increase, is actually log of n. Maybe I'll create a separate video of how this is increasing with log n. Maybe you can try it yourself, that if you can see that why I'm saying that this will only take log of whatever is the value of n. So from wherever you will start, if idx is 0, and even if your n is 10 to the power 6, it will only take logarithm of 10 to the power 6 to reach to the last index. Same with here, because here we are decreasing, maximum it will take log of n here also, right? So I will in separate video I will do the complexity analysis of it. I just want to keep it very simple, because Fenwick itself people don't study that much, because they find it very difficult to understand Fenwick. So I want to keep this video very simple. Thank you very much, guys. See you in another video. Take care. Bye.